Let us consider an example to construct the SVD decomposition of a rectangular matrix A. We would like to write the matrix A as a multiplication of the three matrices U, sigma, and V, where U will be K by K matrix, V will be N by N matrix, and they are orthogonal matrix, namely their columns are orthonormal, and sigma will be diagonal matrix, which has on its diagonals the singular values. Let A is equal to 1, 1, 0, 1, 1, 0. In the beginning, before we start, we need to see what will be the size of the A transpose to the A and AA transpose. If we multiply A transpose to the A, we're going to have a 2 by 2 matrix, and if we multiply AA transpose, we're going to have a 3 by 3 matrix. So it is better to start with finding the eigenvalues and eigenvectors of this 2 by 2 matrix because it is smaller. In the first step, we need to multiply this matrix and find its eigenvalues. Let A transpose to the A is equal to 1, 1, 0, 1, 1, 0. Multiplied to the 1, 0, 1, 1, 1, 0. If we multiply the first row to the first column, we get 2. The first row to the second column, we get 1. The second row to this first column is 1. The second row to the second column is 2. So we have the symmetric matrix with 2 by 2 size. So in order to find the eigenvalues, we need to solve the characteristic equation. Determinant of the matrix minus lambda I should be equal to the 0. So basically we need to subtract lambdas from the diagonal entries of this matrix, which will be 2 minus lambda, 1, 1, 2 minus lambda, and its determinant should be equal to the 0. Basically we need to multiply these entries minus this multiplication. 2 minus lambda in the square is 4, minus 4 lambda plus lambda square minus 1 should be equal to the 0. Then we have lambda square minus 4 lambda plus 3 is equal to the 0, which leads to this equation. We can write them as a multiplication of the lambda minus 3 and lambda minus 1 in D is equal to the 0. So that is why the first eigenvalue will be equal to the 3. The second eigenvalue is equal to the 1. It is important that we choose the biggest eigenvalue as the first one and the smallest one as the second one. We always need to choose the eigenvalues in descending order for the singular value decomposition. So in the second step, we need to find the eigenvectors of this matrix. In order to solve this, to find the eigenvectors, we need to find all kind of vectors x so that this equation is true. Basically, we multiply this matrix for lambda 1 and lambda 2 and multiply this to some vector x, and it should be equal to the 0 vector. All kind of these vectors will be the eigenvectors of the A transpose to the A. So we will do this for lambda 1 and lambda 2. So for lambda 1 is equal to the 3. If we subtract from it the diagonal entries of this matrix 2, 1, 1, 2, the 3, the lambda 1, it will be minus 1, 1, 1, minus 1. So this matrix is obtained by just subtracting the 3 from the diagonal entries of the A transpose to the A. If we multiply this to some vector with the components x1 and x2, it should be the 0 vector, and we need to find all possible vectors with the components x1 and x2. So basically, we need to find the null space of this matrix. In order to do this, we need to do the reduction by just adding the first row to the second row. We obtain 1 minus 1, 1, 0, 0, multiplied to the x1 and x2 is equal to the 0, 0. So this is already in the row echelon form, where minus 1 will be the pivot. So that is why the first column is the pivot column, and the second column is the free column because it doesn't have the pivot. So that is why we choose the x2, which is the free, is 1. And if we multiply the first row to the first column and equalize this to the first row from the right hand side, we have the equation x1 with the minus plus x2 is equal to the 0. If we substitute x2 to be equal to the 1 to here, we got a vector with the components 1 and 1. So this is the first eigenvector of this matrix 1 and 1. So before we choose this as the column of the V matrix, we need to normalize this. So V1 will be x1 divided to the x1 norm. So if you remember, the norm of the x1 is every component in the square and their sum, and we need to take the square root. Basically, it will be x1 divided to the square root of 2, or we can simply multiply x1 to the 1 over square root of 2. So this vector is the unit vector, and which has the same direction as the first eigenvector. So we need to find a unit eigenvector for the lambda 2, which is equal to the 1. So if you subtract the 1 from the diagonal entries of the A transpose to the A, we're going to have a matrix 1, 1, 1, 1. So this matrix now is obtained by subtracting 1 from the diagonal entries of this matrix. Then we need to find such a vector with the two components x1 and x2 so that it becomes 0 and 0. So in order to do this, we need to find the null space of this matrix, and we start with the reducing of this matrix by just multiplying the first row to the minus 1 and adding this to the second. We obtain the matrix with the 1, 1, 0, 0 components. If we multiply this to the x1 and x2, we get 0 and 0. Again, the first column is the pivot column, and the second one is the free column. So that is why we can choose x2 as anything, but we usually choose this as 1 because we would like to have the uniform solutions for everyone. So now, if we multiply the first row to the first column and equalize this to the 0, we got the equation x1 plus x2 is equal to the 0. By substituting x2 to the second equation, we will get x1 is equal to the minus 1, x2 is equal to the 1. So this will be now the second eigenvector, minus 1 and 1. By just normalizing this, we obtain the second column of the matrix V. So V2 will be x2 divided to the norm of the x2, which is again 1 over square root of 2 multiplied to the x2, which is minus 1 and 1. So in the next stage, we need to find the singular values. As you remember, we talked about this, so we say that we would like to denote the norm of the multiplication A to the V as sigma, basically. If I multiply V1 to the A, it will be sigma 1. If I multiply the V2 to the A, it will give me the sigma 2. We can obtain this sigma 1 and sigma 2 differently. So do you remember V was the eigenvector of the A transpose to the A? Namely, if I multiply this matrix to the V, it should be a similar vector, which is just multiplied to some constant lambda. Let me now multiply both sides to the V transpose from here and from here. Then we obtain the equation V transpose to the A transposed multiplied to the AV, which will be equal to the lambda multiplied to the V transpose to the V. As you remember, we can write this down as the A multiplied to the V transposed multiplied to the AV, and it will be equal to the lambda, and this is nothing else as the norm of this vector in the square. So this is again the norm of the AV in the square, and this is equal to the lambda multiplied, since V is the unit vector, its length is equal to the 1, and the square of its length will be also 1. So that is why, since we denoted this as the sigma, it will be equal to the sigma square is equal to the lambda. So that is why the sigma is equal to basically the square root of lambda. Okay, so now let us multiply A to the V. We need to do this anyway in order to find the U. So A multiplied to the V1. A was 1, 1, 0, 1, 1, 0. multiplied is a 1 over square root of 2, 1, 1. Basically, we need to add 2 columns and multiply this to the 1 over square root of 2. 1 over square root of 2. Addition of this column to this column will be 2, 1, 1. So the norm of this vector, 1 over 2, 2, 1, 1, can be obtained by just taking out this constant and finding the norm of this vector ln. So this will be 1 over square root of 2, 2 in the square plus 1 in the square plus 1 in the square from the square root, which is square root of 6, and it will be square root of 3. Do you remember it was the same as the square root of lambda 1 because the lambda 1 was 3. So if I normalize this vector, I can find the u1. So if I multiply the a to the v2, it will be, so this will be now the sigma 1. A multiplied to the v2 is 1, 1, 0, 1, 1, 0. Multiplied to the 1 over 2, multiplied to the minus 1 and 1. Basically, we need to multiply this column to the minus 1 and this column to the plus 1 and add them. So we will have here 1 over square root of 2 is there, 0, 1, minus 1. So we can see that the norm of this vector is actually equal to the 1 because the 1 over 2 multiplied to the norm of the 0, 1, minus 1 will be equal to the 1 over 2 multiplied to the square root of 2, which is equal to the 1. I take this as the sigma 2. So as you remember, lambda 2 was equal to the 1, so actually this is equal to the square root of lambda 2. So basically we can find the sigma 1 and sigma 2 by taking the square roots of the eigenvalues of the A transpose to the A. So in the next step, in step number 4, we need to find the eigenvectors of the AA transpose, and you know we can find the U1 and U2 as just dividing AV to the sigma. So that is why U1 will be, we already know what is AV1, right? So 1 over sigma 1 multiplied to the AV1. So sigma 1 was 1 over square root of 3. AV1 was this vector. So we put this here, 1 over square root of 2 multiplied to the 2, 1, 1, which will be equal to the 1 over square root of 6, 2, 1, 1. So in order to find the U2, we do almost the same thing. So 1 over square root of 2, AV2 is equal to the 1 over 1 multiplied to the 1 over square root of 2. So this is the AV2 multiplied to the 0, 1, minus 1. So now we have 2 eigenvectors of the A transpose as well. We can write now the A as the U sigma V transpose. By just putting the columns U1 and U2 to here, it will be 2 over square root of 6, 1 over square root of 6, 1 over square root of 0, 1 over square root of 2, minus 1 over square root of 2, multiplied as a sigma, square root of sigma 1 was square root of 3, 0, 0, 1, multiplied as a V1 transpose and V2 transpose. Actually, we put the V1 as the first row, 1 over square root of 2, 1 over square root of 2, and we put the V2 as the second row, because here we need to write the V transpose. So we have the SVD decomposition, but since the U is not a square, we call the singular value decomposition as reduced singular value decomposition. This is called reduced just because the U is not square. So it is 3 by 2 matrix, this is 2 by 2 matrix, this is 2 by 2 matrix. If we do this multiplication, we will get exactly the matrix A. However, for some of the applications, we need the U to be square because it will be easier for us to make the diagonalization of the A, because the U will be square and the inverse will be simply U transposed. So we now need to make the U to be square. We can make this square by just adding the third column, which will be perpendicular to the U1 and U2. So we choose U3 as orthogonal to U1 and U2. So do you remember, we can write this as the scalar multiplication of the U1 to the U3 should be equal to the 0, and the scalar multiplication of the U2 to the U3 should be equal to the 0. We can put this as a matrix equation where U1 transpose will be the first row, U2 transpose will be the second row, multiplied to the U3 is equal to the 0, 0. So now this system of linear equation is equivalent to this matrix equation because when we multiply the matrices, the first row to the first column, U3 will be equal to the 0. The second row multiplied to the first column U3 will be equal to the 0, which is equivalent to this system of linear equations. So now, do you remember U1 and U2 was difficult numbers with the radicals? We can actually write them without radicals. So we can write the 2, 1, 1, 0, 1, minus 1. So this will be U1 and U2. The reason why we can leave those radicals is that if the vector U3 is orthogonal to these two vectors, then they will be orthogonal to the actual U3, U1, and U2 as well. So geometrically, we can show it like this. So let's assume that this is our unit vector U1, and we are looking for the unit vector U3, which will be orthogonal to the U1. So now, if I just multiply U1 to some constant to make it longer, because it will be easier for me to work with this vector, it will be, in our case, U1 multiplied to the square root of 6, right? So U3 will be still perpendicular to the black one as well. So basically, 1, 1, 0, 1, minus 1 multiplied to the x1, x2, and x3, and this should be equal to the 0 and 0. Basically, we need to find the null space of this matrix. In order to do this, we need to do the reduction. So I see from here that this is the pivot, and this is the pivot because they are the first non-zero entries on their rows. And I need to eliminate this entry. In order to do this, we need to multiply the second row to the minus 1 and add this to the first one. We obtain 2, 0, 2, 0, 1, minus 1 multiplied to the x1, x2, and x3, which is equal to the 0, 0. So at every step of the elimination, the system of linear equations, this one and this one, have the same solution. So now, this is already in the row echelon form, and we can try to solve this. So since the first column and the second column have the pivots, the third column has no pivots, so that is why it is called a free column. So that is why x3, the third variable, will be the free, and we can choose this as 1 by ourselves. The first row to the first column gives us 2x1 plus 2x3 is equal to 0, the first row on the right hand side, and the second row to the first column gives us x2 minus x3 is equal to the second row on the right hand side, which is 0. So we can try to solve this. If I substitute x3 to the second equation, we obtain that x1 is equal to the minus 1. If I substitute the x3 to the third equation, we'll have the x2 is equal to the 1, and x3 is equal to the 1. So this is the vector which is perpendicular to the 2, 1, 1, 0, 1, minus 1. We can simply check it easily by just multiplying minus 1 to the 2, 1 to the 1, 1 to the 1, it will be 0, the sum. Minus 1 to the 0, 1 to the 1, and 1 to the minus 1 is also 0. So we can take the U3 as normalized version of this vector. So basically the norm of this vector, which is 1 over from the square root, minus 1 in the square, plus 1 in the square, plus 1 in the square, multiplied to this factor, minus 1, 1, and 1. It will be 1 over square root of 3, minus 1, 1, and 1. So I can choose this as the third column of the U. So then now SVD decomposition becomes 2 over square root of 6, 1 over square root of 6, 1 over square root of 6, 0, 1 over square root of 2, minus 1 over square root of 2, minus 1 over square root of 3, 1 over square root of 3, 1 over square root of 3, multiply it as a sigma, and multiply it as a V1 transpose, which was 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2, and 1 over square root of 2. It will be the V transpose. Now, so this matrix becomes 3 by 3 matrix, this matrix becomes 2 by 2 matrix. So actually the sigma should be 2 by 3 by 2 matrix so that I can do this multiplication. So as you remember, it was sigma 1, 0, 0, 1. Now I need to choose the third row so that it doesn't change my previous decomposition. So it should be the same still to be equal to the A. So I choose this here 0, 0, so that I will get the A in the right hand side part. So now this is called the singular value decomposition of the rectangular matrix A.